using Ampere circuital theorem or circuital law, we are going to find the magnetic field due to an infinite straight current carrying conductor. Let us consider a current carrying conductor, and this is the one portion of that infinite conductor. We take a portion of that infinite current carrying conductor. This is that portion, right? This is that portion of the conductor. It is infinite, right? And this is the axis of the current carrying conductor, and radius of this current carrying conductor is A. This is a portion of the current carrying conductor, this is the axis, and radius of the conductor is A. Now let us say I steady current flows through it. The current produces a magnetic field, concentric circles. The magnetic field lines are concentric circles with the center on the axis. We have already discussed that. Now we are going to find the magnetic field in three different points. First, we take the field point outside the conductor. Second, we will take the field point on the surface of the conductor. And in third case, we will take the field point at the inside of the conductor. Let us, in the first case, we take the point at the outside. At a distance r, P is the field point, where r is greater than E. That is, field point is outside the conductor. Case 1, field point is outside the conductor. We take a closed path. We take a closed circular path of radius small r centered at the axis. This is the closed path. Then, according to Ampere circuital law, you can write closed integration B dot dl is equal to mu naught I, because the total current, the current flowing through the conductor, which is I, is enclosed by this path. And already we have discussed that field lines will be concentric circles. Therefore, B and dl are parallel. Therefore, we can write closed integration B dl cos 0 is equal to mu naught I. And also, we can say that B is only depends on the distance of the field point from the conductor or from the axis of the conductor. That means it only depends on this R, right? Since R is same at each and every point of the path, since we have taken the closed path as circle, therefore R is fixed, then B is fixed at each and every point of the closed path, and it can be taken out of the integration. Therefore, closed integration dl is equal to mu naught I. Now, closed integration dl is the total length of the path, and which is 2 pi r. Therefore, this can be written as B into 2 pi r is equal to mu naught I. Therefore, B is equal to mu naught I by 2 pi r. Or we can say mu naught by 4 pi to I by r. Now see here, B is proportional to 1 by r. As the distance from the conductor increases, a magnetic field will decrease. The magnetic field lines are case 2. The field point is at the surface of the conductor. And in this case, just we can put R is equal to A. And for that case, B is equal to mu naught I by 2 pi A, or you can write mu naught by 4 pi 2 I by A. This is the field at the surface of the conductor. Now, if the field point is at the or is inside the conductor, let us say this is the field point, right, which is at a distance r from the axis of the conductor. Field point is at a distance r from the axis of the conductor, and r is less than a, that is less than the radius of the conductor. In this case also we have to take an Amperian loop, that is a closed path which is taken as the circular center at the axis. We have taken a circular closed path of radius small r, which is less than a, center at the axis. This is the Amperian loop. This is the C, closed path C. Now, if the current flows through only the surface, then the current enclosed by this closed path is zero. Is it clear or not? If current is flowing through only the surface of the conductor, then current enclosed by this closed path is zero. Current is outside the closed path. Therefore, I will be zero. Point out these things. If current flows through the surface only, surface of the conductor, then I enclosed will be zero, and for that case, and therefore B will be 0. Now, if the current is uniformly distributed throughout the cross section of the wire, here is current, here is current, here is current, here is current, also uniformly distributed, then there will be a current through this surface. If the current is uniformly distributed, if the current is uniformly distributed throughout the cross section, then current through the cross section of area pi r square is I dash is equal to, what will be the current? For that case, it will be I divided by pi a square into pi small r square. See here, if total current is I, therefore through the cross-sectional area of pi a square, current is I. Pi a square is the total cross-sectional area of the conductor. Therefore, I is the current through the cross-sectional area of pi a square. Therefore, current through unit cross-sectional area will be I by pi a square, and current through pi small r square is equal to I by pi a square into pi r square. Therefore, we can write I r square by a square, and in that case we can write B dl cos of 0 is equal to mu naught I should be written as this. I enclosed will be this. I into r square by a square. And therefore we can write B closed integration dl is equal to mu naught I r square by a square, and therefore we can write B into 2 pi r. 2 pi r is the total length of the closed path. Mu naught I r square by a square. Therefore B will be equal to what? 1 r cancels out. Therefore mu naught I r divided by 2 pi square. Mu naught I r divided by 2 pi square is the magnetic field at a distance smaller, less than the radius of the conductor is this. And see here, in this case B is proportional to R. We have already discussed the magnetic field at outside point, and which is proportional to 1 by R. Now we can plot the magnetic field at different points due to a current carrying conductor. Let us take B magnetic field in the y-axis and R, which is the distance from the axis of the conductor, taken in the x-axis. Then if this distance is R equal to A, then up to A the field is proportional to small r, and it is straight line. It is a straight line. Y is equal to mx, right? And outside the conductor, it is proportional to or inversely proportional to the distance. That means this variation is proportional to 1 by r, and this variation is proportional to r. This is the magnetic field due to an infinitely long straight current carrying conductor at different points, that is at inside the surface, at the outside point.